Hello, my name is John Maddog Hall, and I'm the president of Linux International.
And I'm Steve Mcintyre. I'm an engineer working for ARM, and I'm seconded into Linaro.
And we're here today to talk about a performance contest which Linaro is sponsoring, basically working with the ARM 64 architecture and the GNU Linux operating system. Many, many years ago, when computers were a lot smaller in logical size and a lot slower and a lot more expensive, people had multiple ways of programming, either in a high-level language like Fortran or COBOL or C, or in what we call a low-level language, such as assembly language. The assembly language was specific to a particular processor and sometimes a particular processor family. And therefore, when you wanted to take the code that you'd written in the assembly language to another machine, it was very, very difficult. And you typically had to rewrite the entire code over again for the new machine. With a high-level language, you typically could recompile the program when you took it to another system. People still use assembly language in working with machines relatively recently because it is also very efficient. And if you're very good at writing the assembly language, you might be able to get a significant improvement in the speed of particular processes. However, over time, compilers have gotten better and better. The memories are larger. We don't need to worry as much about the amount of space we use. The cores of the CPUs are multi-core, so that you have 2 or 3 or 4 CPUs on a particular chip, and you might want to be able to use all of them instead of just one. And all of these things lend to moving away from the use of assembly language, except in very, very specific cases, and moving towards high-level compilers. So recently, ARM is bringing out a new chip, a 64-bit version of their system. And they realized that there was a lot of code inside of GNU Linux which had assembly language in it. And Steve did a study of this code and found out that there were over 1,400 different modules that had assembly language in it, and that these would have to be changed to allow it to run efficiently on an ARM 64 computer. So with a bunch of other people, he went through the code and did some analysis of the code and said, well, yes, we could just port this code. We could make it so that it would work on the ARM 64. But we believe that a better thing would be to evaluate the code and say, could we do it better? Could we change, could we do it in a high-level language and eliminate the assembly code for every type of architecture? Could we make it so that we could have what are called intrinsics that would do the same thing, but you would not have to worry about porting it in the future? So we decided to create a contest which is not only about porting the code and making it work well on an ARM 64 processor, but also looking at the basic underlying code to see if we could make it run faster and better for all of GNU Linux and for all of the different architectures. So Steve, I'm going to ask you a few questions because I did read your paper there and I was very impressed by it.
Okay.
And when you started looking through these modules and things, what was the first thing you found out about it?
Well, I guess I'll explain exactly how we started. We basically did an analysis of all the packages in the Ubuntu Linux distribution and in Fedora to see what looked like it might contain assembly to start with. So that was where we came up with this number of 1,400 packages in the end. And that was just a very simple, quick and dirty scan using the obvious tools, grep and things like that. What we found was, in fact, there's quite a lot of packages that look like they might contain assembly, but actually they're false positives. So that's easy to pick out. Thankfully, it reduces our target space. What we then found was that there's a few categories of I guess, reasons why people, have been using assembly in the code. Typically, it's old code that's been around for a very long time. Sometimes it's because people think it's faster. Sometimes it's because people need low-level access to their hardware that isn't available through any normal high-level programming languages. And so I actually set these out into a variety of I think I came up with 6. Yes, 6. So the most common ones were for things like byte swapping for bitwise operations, places where people were doing really, really simple operations that, to be honest, these days a compiler will do much better than, even if you've gone and spent weeks doing your hand-optimized code, you might have beaten a compiler 10 years ago, but these days a good compiler will recognize it and will be able to substitute something that's probably better than what you did. We then have, as I mentioned, things like low-level hardware access, people wanting to know which particular flavor of CPU they're running on. Although for most things it shouldn't really matter anymore, if your code is good. And in those cases, again, it would be awesome if there was a more generic, if there was library code, or as you say, or intrinsics, to be able to find out this information. People wanting to get access to timestamp counters, if they want, which are great if you want to do very, very detailed analysis and profiling of your code's performance normally, but actually in normal day-to-day use, nobody really cares. There's SIMD, so single instruction, multiple data. Places where people are using lots of this would be in multimedia code, obviously, where they want to be able to use the latest, greatest hardware that's available on modern Intel, ARM, PowerPC, everybody's CPUs now, to be able to get the best performance for doing large amounts of data manipulation. Again, there are better ways than doing that in assembly. There are already intrinsics available in the compilers to be able to do this, but 10 years ago there might not have been. It's basically the same thing that keeps on coming up over and over in lots of these cases. There are better ways of doing it now that people may not have actually been able to find years ago.
I know that from my own personal experience that there are flags on the GNU-C compiler that weren't there, 10 years ago.
Exactly, yes. And but of course there's also the experts who work on the compilers, have been working on these things. The toolchain guys haven't just been sat around, watching the world go by. These are exactly the places where the really, really scarily intelligent people have been, working their darndest to try and improve the state of the world. We should be making the most of what they've done.
Right. So what we're trying to do with this is we're trying to allow the community to work together, both the upstream maintainers who are maintaining the code, with also people who would be very interested in learning more about optimization techniques, more about how to write, what the code's doing and how to use the compilers in a better way. And if it is determined that the best way of doing this is to write the code again in assembler, well, that's fine too. But we would like to see some performance improvement come out of this and to clean up a lot of this code and make it better and perhaps more portable. So we actually have 2 parts to the project. One part of it is strictly porting the code to ARM64, making sure that it works on ARM64. And if that's what people want to do, then they will submit their code to the upstream developer. The upstream developer will approve it, and it will go into the code base. At that point, the person who did the work will go into a contest drawing to be able to come to a Connect meeting or get some other type of prize. And this will be done in the official rules, stated in the official rules. The second part is the performance part, where we will have a contest to see who gets the greatest improvement in performance of the modules which they work on. And this might be done by using more of the options of the compiler to make the compiler do the job better. It may be something like replacing the algorithm with a more modern algorithm. But what we don't want is we don't want any performance improvement to be at the detriment of some other architecture. So we don't want people going and say, oh, I know I can do this great on ARM, but when I rewrite the code, it's going to make Intel look terrible. We don't want that. We want this to improve the performance of GNU Linux across the board. And we feel that this is a good thing for the GNU Linux community. And we feel that it's something that can continue on into the future, even after all of the code is working on ARM64. There are many interesting pieces of hardware which are coming down. Field programmable gate arrays, digital signal processing chips. And we feel that these could be used to increase the performance of GNU Linux systems dramatically if people really understood what they did and how to use them, and particularly turning them over to high-level languages which were completely developed to take advantage of these types of chips. So this is the ARM and Linaro Performance Contest, and we would encourage you to take a look at this, to read the rules, and decide whether you wanted to participate in this, whether you be a university or university student or a professional programmer, or whether you be an amateur programmer, to be able to learn about this and to develop a portfolio of work that you have done because it's open source that you can show to prospective employers. So there's a lot of reasons to participate in this particular contest, and we hope to see you working on it. And thank you very much.